Hello and welcome to this presentation on differentiation applications. We're going to review turning points.
So here's an overview of the presentation related to calculating turning points. It's the maximums and minimums, also referred to as maxima and minima turning points. We commence with an introduction, defining turning points and also points of inflection. Next there is an outline of a four-step method used for solution of turning points. Then we have example 1. Here's our quadratic equation that we solve for one turning point. Then we have exercise 1. Here's a cubic equation that we solve for two turning points. Next we have an array of tutorial questions that are overviewed and various hints are stated to help you solve these questions. No solutions to these questions are included here. We then have example 2, which is a turning point application calculating the maximum volume associated with a rectangular steel box. And finally we have exercise 3, again another turning point application problem. This time we're trying to determine the minimum surface area of a cylinder. The full work solution to example 2 and exercise 3 are included in the presentation. And for your reference, here are the approximate start times related to the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note all times are generally rounded to the nearest minute. Note for reference that turning points are considered to be a local maximum turning point or local minimum turning point within our solutions, but turning points are also called stationary points, essentially an umbrella heading that also includes points of inflection. We will define turning points and points of inflection in the presentation. And just note for reference, the word inflection shown here is the traditional English spelling, but in some more modern textbooks it's often written with the American spelling shown here. Again, that's just for reference.
Okay, some reference information here. This presentation assumes you understand how to find standard derivatives from a standard table, given a function of y, find a dy by dx, and also to use successive differentiation. So given function y, we can differentiate it to find the first differential, dy by dx, or function dash x, and to find the second differential, d2y by dx squared, or function double dash x. Okay, turning points, sometimes referred to as peaks and troughs, or buckets and hats. In figure 1 here, we have two turning points, one at P and one at Q. If you look at the gradient prior to point P, you can see that it's a positive sense. So the gradient as we go increase towards P is reducing its positive sense until we get to P, when we have a zero gradient at the top of the curve. As we move away from P towards Q, the gradients now become increasingly negative. And this is what defines what's called a maximum. If we look at point Q here and the gradients prior to point Q, we can see we have a negative gradient that is decreasing as we get to Q. At Q we have a zero gradient at the turning point itself, and as we go past Q towards R, the gradient then becomes a positive gradient. And this defines what's called a minimum. So when your gradient is decreasing in a positive sense and then increasing in a negative sense after a turning point, we have a maximum, and when it's decreasing negative prior to the turning point but increasing positive afterwards, we have a minimum. In figure 2 we have maximums and minimums considered. We have maximums here and here. These are maximum turning points. Again, the gradients before the turning point are decreasing in their positive sense, and afterwards they are increasing in a negative sense. So for both maximums that's true. And if we look at the minimum, one minimum here, the gradient prior to the turning point is decreasing in a negative sense, and afterwards an increase in the positive sense. So we have maximums and minimum turning points. We also have something called a point of inflection here and here. Now points of inflection are where you have, so this point of inflection here, you have gradients of negative sense decreasing to zero, but it's still a negative sense gradient afterwards that's increasing. So it doesn't go from negative to positive. In this case it's gone from a negative gradient to zero to a negative gradient afterwards. And with this point of inflection, we've got the opposite. We've got a positive gradient prior to the point of inflection, decreasing in its sense to 0, but then it's increasing in the positive sense afterwards. So that's a point of inflection.
So just to clarify, we have turning points that can be a maximum or minimum, or we can have a point of inflection. And just note that maximums and minimums and points of inflections can all be termed stationary points.
Okay, we're going to consider maximum, minimum and points of inflection values and their relationships to differential equations. If we're given a function of y and we plot it and it looks like this with a maximum at a, that's x1, a minimum at b, that's x2, and a point of inflection at c, x3, if we differentiate the y with respect to x to get the first differential equation, the f dash x, what we notice now at x1 on the dy by dx we have 0, at x2 on the dy by dx we have 0, and on the x3 on the dy by dx we have 0. In other words, the dy by dx is 0, the gradient is 0 at x1, x2 and x3. So we must have by definition turning points at these three positions. But what the dy by dx curve doesn't say is whether the maximums, minimums or points of inflection. We only get that by the graphical method. So if we didn't have the graph to review, we would have to use the second differential to help us decide if at these turning points we have a maximum, a minimum or a point of inflection. So when we differentiate the equation again to get the d2y by dx squared and put the value of x1 into it, we end up with a negative value. I'm not bothered about the magnitude of that value, just the fact it's negative. When we put an x2 into the d2y by dx squared, we get a positive value. And again, I'm not bothered about the magnitude, it's just positive. When we put the x3 into the d2y by dx squared equation, we get 0. So what the d2y by dx squared equation does is tells us if we've got a maximum or minimum or point of inflection. So essentially, using the d2y by dx squared equation, if we put the value of x into it and we get a negative value, we have a maximum. If we put a value of x into it and we get a positive value, we have a minimum. And put a value of x into it and we get a 0 value, we have a point of inflection. Okay, we're going to look at a process here for locating and distinguishing between the stationary points of maximum, minimums and points of inflection. So the first step in this process, we're given y is some function of x. We are going to determine the first differential dy by dx, or f dash x. The second step, we're going to let the dy by dx equal to 0, which is where turning points occur, and we're going to solve the resulting equation. Now at this stage here, sometimes a quadratic equation can occur. So sometimes you may need to use factorisation or the formula to solve at this stage. In other questions, it may be a direct solution. Step 3, once we've found the values of x from step 2, we simply put them back into the original equation, the y is a function of x, and we will find the y coordinates. So this then defines the actual location of the turning point in the x and in the y. Continuing the process, up to now we've found where the location of the turning points occur in x and y, so we've defined their locations, but without a graph we do not know if they're maximums and minimums. And this is where the second differential comes into play. If we then differentiate the equation again and get the d2y by dx squared equation, we substitute the values of x we have from step 2 above into this equation. If the value of the d2y by dx squared is positive, we know we have a minimum. If the value of the d2y by dx squared is negative, we know we have a maximum. And if the value of the d2y by dx squared is 0, we have a point of inflection. There is another way of checking for maximums and minimums, which is more numerical. This is where you put values associated with the x values into equation 2, and you look for a change in gradient. So if your x value was, say, 3, you might put 2.9 in, check the gradient, put 3.1 in, check the gradient. If you've got a positive to a negative gradient, you've got a maximum. If you've got a negative to a positive gradient, you've got a minimum. And if you've got, say, a positive to a positive gradient, you've got a point of inflection. I'm not going to use this method in this presentation. Okay, example 1 here. We're now going to go through an example using the previous process outlined. So we're given a function y equals x squared minus 4x plus 4, and it's been plotted for us for reference here on this diagram. We can see on the diagram visually that we seem to have a turning point at x equals to 2 and y equals to 0, and it's obviously a minimum value. In most of the questions in this presentation, there aren't graphical representations given. So step 1 in this process, given the equation y equals x squared minus 4x plus 4, which I've called equation 1, I'm going to differentiate. I'm going to find the first differential, the dy by dx. So from standard tables, x squared differentiated becomes 2x, minus 4x differentiated becomes minus 4, and the constant plus 4 disappears. I've called that equation 2 for reference. Step 2 of our process, we're going to equate to 0 the dy by dx equation. So I've got 0 here for dy by dx. It equals to 2x minus 4. In this case, this is a direct solution. Just by rearranging the equation, we can solve for x. So adding 4 to both sides and dividing by 2, the x location is 2, which of course we can clearly see from the diagram above. To find the y coordinate now, in step 3, we go back to equation 1 here, and we simply put the value of x into equation 1. So y is equal to x squared, so now that's 2 squared, take away 4 times x, so that's 4 times 2, and plus the 4. We do the numbers on that, we find that the y coordinate is equal to 0, and again we can see from the graph y is equal to 0. So we found the stationary point and the coordinate of 2, 0 for that location. What we do not know at the moment is if it's a maximum or a minimum, without the graph. Okay, from the previous slide we found that we've got a turning point at x equals to 2 and y equals to 0. Without the graph, we wouldn't know if that was a maximum, a minimum, or a point of inflection. So in step 4, we find the second differential of our function, differential equation 2, which is dy by dx is equal to 2x minus 4. And when we do that to get our d2y by dx squared, we find the value is 2. Now that's a positive value, so that's a minimum by definition. And of course we can clearly see we've got a minimum on the graph. Exercise 1 will take you through here a slightly more complicated equation. It's actually a cubic, y equals x cubed minus 3x plus 5. And again, just for this exercise, I've plotted the curve here so we can see its function. We can see that at x equals to minus 1, we have what looks like a maximum there, and x equals to plus 1, we have a minimum. So just by looking at the graph, we look like we have a maximum at minus 1 and possibly plus 7. And we have a minimum at plus 1 and possibly y is equal to 3. But the process we're going to go through now will confirm that for us. So step 1, we're given the equation of y equals to x cubed minus 3x plus 5, calling that equation 1 there. We're going to differentiate it to find the first differential. So y dash is equal to 3x squared minus 3. So again, standard forms there. X cubed differentiated gives you 3x squared, minus 3x differentiated gives you minus 3, and the constant disappears. I've called that equation 2. Step 2 of a process, we equate equation 2 to 0, and we solve the resulting equation. So 0 on the left hand side here is equal to 3x squared minus 3. This is quite an easy equation to transpose. So adding 3 to both sides and then dividing both sides by 3, we get x squared is equal to 1, and then x is equal to the square root of 1. But don't forget, when we take a square root, there's always two answers, a plus and a minus, so the solution here is plus and minus 1, which of course we can see from the graph. We've got a turning point at plus 1 and a turning point at minus 1. Here I've just repeated equations 1 and 2 for convenience. So step 3 of our process, we found the value of x for the turning points. We need to find the value of y now, so we're going to use equation 1 for this. So for the value of x is equal to 1, we simply put 1 into equation 1 wherever we see an x. So it's y equals x cubed, so that'll be 1 cubed, take away 3 times x, so take away 3 times 1 plus the 5. If we do the arithmetic on that, we will see that y is equal to 3. And then to find the y value for the second value of x, the second turning point location, x equals to minus 1, again using equation 1, put the value of minus 1 wherever we see an x in the equation. Just be careful with the negative. Negative 1 cubed is negative 1, and we've got a double negative there in front of the 3. But that gives us y is equal to 7. So now we've found our two turning points or stationary points. The first one is that x is equal to 1, y is equal to 3, and the second turning point is x equal to minus 1, y is equal to 7. However, without the graph, we wouldn't know if they're maximums and minimums. So we use step 4 here to find out whether they're maximums or minimums. So the step 4 requires us to find the second differential. So we've got our first differential, the y dash equation is 3x squared minus 3. from equation 2 above. So find the second differential y double dash here. That would equal to 6x from standard form. So 3x squared becomes 6x and the minus 3 constant disappears. I've called that equation 3. So to find if we've got maximums or minimums, we simply put the value of x for each of our coordinates into equation 3. So y double dash is equal to 6 times x, so when x is equal to 1, that will give us a positive value of 6. I'm not bothered about the magnitude, just the fact that it's positive, because that means it's a minimum turning point, and if I put the value of minus 1 into equation 3 for the y double dash, I get a value of minus 6. Again, it's irrelevant the magnitude to me, but because it's a negative value, I've now got a maximum turning point. Okay, I'm going to leave you with a few tutorial questions to have a little look at. Just going to give you some hints to them here. Question 1 is a very standard process. We've been to that similar process on the examples, so I'll leave you with question 1 to have a look at. There's one turning point. Question 2 has 5 subparts to it. For part A, you'll find that's a direct solution. There will be 2 turning points, and you'll end up with taking the square root of plus or minus 1. For part B, you will end up with a quadratic equation to solve. So I'll leave you to solve that, so be aware of that. Question C actually has complex roots, so for the point of view of this exercise, you can ignore question C unless you understand complex numbers. For part D, you're going to end up with a quadratic equation, and part E, when you expand it, don't forget to expand the brackets here, it's not in a form yet you can directly solve, so expand the brackets first of all, and that's a binomial bracket. 6 minus x all squared is 6 minus x times 6 minus x, so be careful there. But then you will end up with a quadratic equation to solve. Questions 3 to 5 are very similar to the previous questions as far as the numerical work is concerned, but they're kind of wrapped up in a context here. So question 3 in this particular case is to do with the power consumption. They've given you an expression in terms of P and V here, so notation has changed. Instead of having Y and X, we've got P and V, but standard form here, we've got V to the minus 1 there, that's like an AX to the N type of function. So don't get confused by the context. It's really the same kind of process, same kind of solution that you've been through in the previous question. It says to find the rate of least working in the question, so don't forget that will be looking for a minimum. Question 4 again is standard form type of question. Y equals to 4 theta plus e to the minus theta. That standard form, 4 theta is like 4x, and then e to the minus is like e to the minus x. So they're all standard forms. The 4 theta is the form ax to the n, and the e to the minus theta is the form e to the ax. So I'll leave you with those standard derivatives to deal with. And again, question 5, just be careful with question 5, it's in terms of a cost here. It's x plus 90 times 10 to the 3 divided by x. I suggest use the indices there and bring the x to the top line and make x to the minus 1 before you start the process. But again, you're looking for the least cost in that case. Okay, example 2 here, slightly more complicated problem. In this case, we have to actually generate the equations before we can go on and actually work out the turning points. So the context here is a small box. It's to be made from a rectangular sheet of metal, which is 0.36 meters by 0.24 meters. We're going to cut 4 equal square corners from the sheet of metal, and then we're going to fold up the sides to form the box. We've got to determine the length of the sides of the square corners that we need to cut from the box to make sure we get a maximum volume, and we have to calculate this maximum volume. So drawing a diagram of the information in the question, the length of the sheet is 0.36 meters, the width of the sheet is 0.24 meters. I'm going to cut square corners from the box, and I've labelled the height of these corners x. Okay, so there's my basic diagram from the information given. Now with these kind of questions, you've got to think through what kind of equations are relevant here, where they're talking about volume in the question, so I think I need to work out the volume of the box in terms of my symbols above. Now using my symbols, the volume would be B times L, that would be the area, if you like, of the box we're forming, and then X in this case would be the height of the box. So B times L times X would give me the volume of the box. Again, from the diagram above, the dimension B in this case is going to be 0.24 take away 2x, so x take away x here, gives me the 0.24 take away 2x, and then the length dimension from above would give me 0.36 take away 2x. Again, think that through for yourself above how we get these equations, but that's how we get the B expression in terms of x and the L expression in terms of x. To find the volume of the box V now, I simply multiply my B times my L times my X. My B is 0.24, take away 2x. My L is 0.36, take away 2x, and that is all times x. If I expand the brackets, I will get this expression here of the 0.0864 minus the 0.48x minus the 0.72x plus 4x squared, and you can simplify the terms there inside the brackets, the like terms, and don't forget that is still all multiplied by x outside the bracket. Example 2 continued from the previous page here. So this is the expansion of the two brackets, just repeat it for convenience, and it's multiplied by x here. So step 1 of my turning point process is I'm going to write down my equation, for this case for volume. So expanding the bracket above, multiplying every term by x, I get 0.0864x minus 1.2x squared plus 4x cubed. I've called that equation 1. We need to differentiate equation 1 here to find the, in this case, dv by dx term. I've simply called it the dash for convenience. So differentiating 0.0864x, that will give me 0.0864. Differentiating the minus 1.2x squared gives me minus 2.4x. And differentiating the plus 4x cubed gives me plus 12x squared. All standard form, all ax to the n. Step 2. We need to equate this equation now, equation 2, to 0 to find the turning point. Okay, so taking equation 2, equating it to 0. Notice this is a quadratic equation. It's in the form of y equals ax squared plus bx plus c. And be very careful how you extract your a, b's and c's. A in this case is the plus 12. B in this case is the minus 2.4, associated with the x there. And the c, the constant, is the 0.0864. Just be careful how you extract the terms. And then when you put them into the quadratic equation, don't forget you get a double negative because of the minus b. And in this case we have a minus 2.4. And don't forget when you square a negative, you get a positive value for the b squared there. If you do the arithmetic on that, you get a value of 0.047 meters as one solution from the quadratic. But don't forget there's always two solutions, and we get 0.153 meters also. In this case, from the practical context of the question, only the 0.047 meters is a realistic value. We cannot use the 0.153 meters in this case. Okay, example 2 continued here. Just repeated equations 1 and 2 here for convenience. Continuing on with our process, step 3 in this particular case now, we need to find the turning point, location of it. We know that x equals to 0.04 meters from the previous question. So going back to equation 1 here for volume, we simply put the value of 0.047 wherever we see an x in equation 1 and do the numbers on this. We find that the volume is 0.00183 meters cubed. Okay, so now for an x value of 0.047 meters, we get a volume in meters cubed given to us. We're asked to find though, is this the maximum or the minimum value, because we really want the maximum value of volume. So we need to now find the second differential of equation 2. So differentiating equation 2, all in standard form, I get my d2v by dx squared term, which is minus 2.4 plus 24x. Again, if you differentiate this, it disappears. Differentiate this, you get minus 2x and then the plus 24x. So that gives me the second differential. I've called that equation 3 here. And all I do now is put the value of x, which is 0.047 meters, into that equation and solve it. It gives me a value of negative 1.273. I'm not bothered about the magnitude. The fact it's a negative value means I have indeed got a maximum volume for these dimensions. Exercise 3 here, very similar to the previous example we looked at. The only thing that's different here, I have a cylinder can here, not a rectangular section in the example. And you're asked to find the minimum surface area here at which you can make this can if it's going to have a volume of 1 meter cubed. So again, the subtleties of this question suggest we need the volume formula for a cylinder, which in terms of diameter is pi d squared h, the height divided by 4. And we'll also need the surface area formula here. So the curved surface area is given as pi dh, and then the area of the two ends of the can will be pi d squared upon 4 times by 2, because there are two of them. So my suggestion here was to use the volume equation. We arrange that for height h. and then substitute that equation into the surface area equation A, so you eliminate the H and you leave yourself an equation in terms of D on the right hand side. You can then differentiate the surface area equation to get dA by dd, equate that to 0 and solve for the value of D for the minimum surface area, and then back substitute it to find the value of H for the minimum surface area. I'll let you have a go of that, but over the page will be the work solution. Exercise 3 here, the full work solution. On the following slides now show you how the turning point question was undertaken. Thank you for viewing.